Good morning, everybody. Welcome back. How's the homework on Bayes going? Some good. Theoretical stuff matching those simulations. Make sure you get all the numbers crossed the right way. And then the two-dimensional, you're seeing lots of different shapes. Graduate students having fun with algebra? Good. Okay. So we're pretty much done talking about the basics of Bayes theory. We went over it again last class, trying to pull you all together. I posted the project. How many of you have seen that the project is posted? Okay, I didn't say you have to look at it. You've seen that it's posted. Yesterday? I think yesterday. That's okay. You had enough stuff to do as a homework. I wasn't in a hurry because if you give students too many assignments at once, you lose track of what you should be doing first. And I want to make sure, even if I tell you what the due dates are, students will lose track of what they should be doing first. I want to make sure you got that homework done first. So I left you enough time to focus on that. How many of you are done with the homework? Good, good job. So then you're all ready for the project. And how many of you have a vague idea what you're doing with the project? A little bit of idea how Bayes works, a little bit. Again, you need to come up with the means and the covariance estimates for each class from your normalized training set. And then you're going to do 4 or 5 different classifiers from there. So it's posted, take a look, reach out if you've got questions. So now we're going to be looking at some ways that are used, and there's lots of different terminology out there for saying how good does pattern recognition work. And you need to be aware of all the different ways of describing the same thing. So there's lots of different vocabulary. So a lot of this is kind of a vocabulary. So we're used to the fact by now of decision matrices, confusion matrices. You have them in project 1. You understand the basic thing. Something goes in, a decision is made, a couple of different types of errors, total % error. But that's not the only way to talk about it. This is the foundation on which everything is built. But this is not just show that and you're done. If you're talking to the general population, this is way too much data. If you're talking to a manager, this is way too much data. You need to be aware of it. You need to be willing to say this is what it is. When you're talking to another engineer, this is where we're at, this is what we're analyzing. This should let you make some decisions about your data. And this is a hint for you to, these results are what you should get on the first thing in your project 2. If you want to make a note, this is what you should be getting. So when you're analyzing it, you'd use a confusion matrix. As a design engineer, you're going to do a lot of analysis. But then you need to say, how do we other ways of describing it? And depending on who your audience is, whether you're talking about other engineers, you're talking depending on the application, depending on whether you're talking in the medical field, you're going to use different vocabulary, which is all consistent with this. But they use some different words that are pulled from here. So let's take the 2-class situation, because a lot of things kind of boil down to 2 classes. Yes or no? Found, not found. Sick, not sick. COVID, not COVID. Tumor, not tumor. So all that kind of boils down into there. And so we could take that confusion matrix and break it into a 2x2 confusion matrix. And we can say that we're starting off with a target absent or a target present. And we detect the target as absent or the target as present. That the tumor is there, the tumor is not there. COVID is there, COVID's not there. any of them. And as you saw in project 1, things on the diagonal are good. Things off the diagonal are bad. But again, even with just a 2x2, this is way too much information for the general public or managers. You need to break it down a little bit. So the first thing is accuracy. This is the same thing you did in project 1. Accuracy is the number of goods divided by the total number. In this little 2x2, A and D divided by A, B, C, D. The same thing you did before. And then the error is 1 minus that, or those two off diagonal ones, B and C, divided by all the numbers. Pretty basic. But again, accuracy is not everything, because sometimes it matters what type of error you're making. That's why we talk about type 1 and type 2 errors. Not all errors are created equal. So we can also talk about these 4 categories as being a true positive, a true negative, a false positive, and a false negative. False positive means it was not there. You were not sick with COVID, but the test said you were. A false negative is you were sick with COVID, but the test said you're healthy, go out and make other people sick. This all boils down to our discriminant functions. And most of it is always couched in the framework of Bayes and Gaussian. So it does not need to have a Gaussian shape, but just about everything assumes a Gaussian shape and works out with that. But any other shape would work and have the same format. So we've got our discriminant functions. We've got one class, which says that you are not sick, but your measurements in your COVID test could have come back anywhere in here. And then the other population is people who were sick, but their measurements on their COVID test could come back anywhere in here. And again, A and D are correct answers. B and C are incorrect answers. And the optimal decision boundary is where those 2 discriminant functions cross. That's optimal, but not always what we want to use. Not all errors are created equal. New terminology, precision and recall. A lot of times results are reported in terms of precision and recall. So both of them are looking at those good, the D's, but the denominators are different. So for precision, we're looking at the number true positives correctly detected divided by all the ones that were said to be positive. So I can get everything correct if I tell everybody that you're sick. If I tell all of you you've got COVID, then I'm totally got everybody in D who should be in D. What's the problem? Precision is low because we made B too big also. Your precision, you were not precise. You could be correct, but not precise. And then recall is that we say that you're there, that you do have COVID. So we're counting all the people with COVID. And we want to know if you have COVID, what group of people who have COVID, what percentage of those people are we able to correctly classify? And they kind of balance. You can have a system designed to have higher precision, but then you'll have lower recall because you'll move the curve. Or you can have higher recall and lower precision. Remington?
Just to be clear, the recall is dividing the total amount of, say, COVID didn't correctly by all COVID cases. And then precision is the ones identified correctly divided by all the ones that were said to be COVID.
Mm-hmm. Correct. And because we can just adjust our figures and force things to give us a high precision or a high recall, but it's sitting on a teeter-totter, you can adjust things, but one goes up, the other one goes down. We quite often put them together and take the harmonic mean of the two. And we call that an F measure, F score, F1 number. Got a whole bunch of similar names, but F, you always hear F in it. I don't know why F, quite honestly, but it is. And so it's just the harmonic mean of precision and recall is your F number, F score, which balances the two. Remington? Harmonic mean is 1 over the 1 over 1 over. It's like parallel resistors. You'll see precision and recall used a lot in the field called information retrieval. Think Google, you're doing a Google search, where precision is the number of return documents that are correct. So Google, if they gave you every possible document out there, they would definitely get you the one you wanted. Right? If a Google search gave you every document out in the world, they would definitely include the one you were looking for. What's the problem with that? Not very useful. So to balance that is recall. How many of those that it gave you are the ones that you wanted? And so when you balance precision and recall, you can then kind of balance the two and get approximately what you want. You want high precision, you want high recall, but you can't really have one without the other. It's always a trade-off. So quite often we want to move that threshold away from that optimal point. There's lots of places you can put that threshold on your curve. And each one's going to change those A, B, C, D numbers. And where you put it is not always going to be in the minimum error, because not all errors are created alike. More terminology, specificity is the same thing as recall, but this is used a lot more in the medical field. And again, it's just a terminology that if you're going to say, I know pattern recognition, you need to be familiar with the terminology that's out there. Because you go start talking with a doctor, a medical person, and they say, well, what's the specificity of your test? You don't want to say, what? So it's the same thing as recall, the D divided by C and D. Out of all the ones that truly were sick, of all the people who truly had COVID, what percentage were they able to detect with your classifier? Sometimes you talk about 1 minus specificity. So rather than looking glass half full, glass half empty, same thing. And then the counterpart to that, whoops, I didn't up this. Sensitivity. I edited it in a different version. And the other part of that is sensitivity, which is going to be your A value, your false terms, divided by your A plus B. So out of everybody who was healthy, did not have COVID, how many of them did they get right? You took a COVID test so you could come back to class after not feeling well. And out of all the people there, when they said you did not have COVID, how many times were they right? Just conditional probabilities. But without the word probability written there, it doesn't seem as scary. You guys can handle it. A lot of people out there can't. So they have other terminology so that these conditional probabilities just don't seem as scary. Okay. So here's something I downloaded from the New York State Department of Health. I'll let you read that. You always want both sides. And in order to get both sides, you need to change your test. You need to change what you're measuring. Because you can move that threshold saying how much of whatever I'm measuring in this test counts. But that's just going to be the whack-a-mole with one side versus the other side. Well, maybe measuring this antigen with this method is not the way of doing it. Maybe I should be measuring this other antigen with this other test, which will measure it differently. And so you then can compare classifiers, and you can never change the balance. You're always going to lose one, win one. The only way to get better is to change your total test. What are you measuring? Because your threshold just pushes error from one side to the other. Again, other terminology, positive detection, reject, probability of a miss, false negative, probability of a false alarm, false positive. Same thing, A, B, C, D. So ROCs, not Republic of China, not if you're in signals region of convergence, ROC, receiver operator characteristic. This is developed in World War II when they're doing pure signal receivers, trying to just do initial transmission stuff, looking at radar. But the idea of it applies to more than just radar, more than just could they find your airplane during World War II using radar. And it is built on statistical foundations, everything is, but a little bit stronger ways. And it's used a lot in a lot of different fields. So it started in World War II radar, but it's morphed because it's so powerful to other things. This is a way of testing all the different possible thresholds. We have those two curves. You can move the threshold, and as you do, your types of errors will change. And this is the way of saying, for my test, for my feature, for my way of working things out, with all these possible different thresholds, which one is better? Is it better to use this antigen test or this antigen test? Not just looking at where you pick the threshold, But if I'm measuring different things, should I use feature 1 or should I use feature 2? Totally changing what you're doing, but we're looking at it across all possible thresholds. Not just pick one and hope that the two balance in the way that you want. So it's going to be a curve over all thresholds, and that shows you the different trade-offs between the different types of errors. So as we move that threshold, we're going to be able to change all these numbers, and we're going to look at a whole bunch of different thresholds. And we're going to plot the probability of detection versus the probability of false alarm. The D's versus the B's. As we move our threshold from one side to the other side. We quite often, because we want to say how good is our test, and I've drawn 3 possible tests. We measure the area under the curve. Our goal is to have perfect detection with no false alarm. This axis is the probability of detection. This is the probability of false alarm. Our goal is to be operating there, where we get perfect detection and 0 false alarm. That's what we want to get. Rarely can you get there. Rarely can you get there. But if we were able to, what would be the area under the curve? 1, because our curve would come up and then over. And that would be perfect prediction. Everything is good. It's not going to happen. But you at least need to know what you're aiming for. If you can get an area of around 0.9, that's like getting an A in a class. That's very excellent. You're doing great. 0.8, you got a good classifier. Nothing to be totally embarrassed about, but it's just good. 0.7 is kind of mediocre. You know, A, B, C, D. 0.5 is this curve here. And that just means you're just randomly guessing. You haven't really done anything. You're selling a bunch of crap to whoever your customer is. And if your area is less than 0.5, you've done something majorly wrong. You'd be better off guessing. These are a couple things you can read at home with just a little bit of extra stuff in there. Our goal is to minimize errors, but not all errors are equally bad. We want to decrease our errors, probability of false alarm, probability of misses. More stuff to read at home. Okay. We can change our curve by changing the distance between the means. If you can pick a feature that separates the means further, it can be better. You can change your curve by changing the standard deviation. Smaller standard deviations are better. And there's a general measure D, which is the difference between the means divided by the standard deviation. And there are 3 possible examples for those curves, what they might look like. So thank you very much Jacob for doing a little bit of running.
Sure.
You need a laptop now, or at least with a partner, one of you needs a laptop. For those at home, look on the internet. The same thing I'm handing out in paper is available, posted in Canvas if you look carefully. I do want you to work with somebody on this. You've got one already. Yeah, she'll be back. I've opened up some breakout rooms for the people at home. There's 2 breakout rooms, which in theory you can get into and out of on your own, in theory. So people at home, I'd like you to eventually leave and go into a breakout room. What I want all of you to do is to call up the signal detection GUI. Maybe not all of you, at least one out of a partner group. I do want you to work with somebody in here. If you're antisocial, become social. Relocate yourself, find somebody. I've met all of you, you're not that bad at people. So I don't care who you work with, you can work in a group of 3 if you really want to, but at least partners. Find somebody you're willing to work with. And I want you to make some ROC curves. On the handout, I specify your system parameters. You're going to test 4 different systems. So you're going to enter in the parameters for A and try a bunch of thresholds and measure your errors. Record them and plot them. Then use the parameters for B. Try a bunch of different thresholds, measure them, report them, plot them. Do the same for C and D, and then compare your 4 classifiers. Is the general idea clear? Glad to know you need a partner. I think you'll work with him maybe. So people at home should be in a breakout room where you can share a screen.
So we're supposed to try with a bunch of different thresholds.
Right.
And then
Each set of thresholds for one set of parameters will make one curve.
Gotcha.
So you'll plot A, B, C, D.
Okay.
And pick 5 or 6 thresholds. Click, 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 change threshold. You'll get those numbers at the bottom of the screen. Plot. You gotta take the false alarm errors, and so they're separated, they're measured down there for you. So increase your N to a higher number, so you get a better estimate. Which it gives you the information. Nope, yours doesn't have that version of the code.
Well, I don't know how to.
Yours had the numbers at the bottom of there, right?
What?
Yeah. Where'd you? So you must have downloaded a different version. Where did you download yours from? The newest version. You've got the circles and the O's. If you download the right version, it tells you which the 2 different types of errors. And She'll have to tell you where she downloaded from. She's got one. If you've got one that has X's and O's, you've got one which should at the bottom of the bottom screen tell you how many of the different types of errors. So if you're,
So his has like,
yeah, you've got it. You're good.
okay.
I must have two versions of it out there someplace.
No, I dropped it off.
Yeah, well anyways, that's the version to use. If it lists everything in there. Does yours show the different types of errors? Yes, yours shows the different types of errors, so you're good. Click on this. Yep, you're good.
I just want to clarify that later. We're gonna change the.
Hey Brent, can you hear me? I'm wondering if they can hear all our recording. It's on the recording now. You guys get anything figured out yet?
Not exactly. I have MATLAB pulled up and I have this up now. I take it we're measuring and recording those circled things on the screen.
Yeah. I'm trying to get MATLAB pulled up. It sucks we can't share our screens.
Yeah.
And this is due during class, so. Okay. Script. Let's copy this shit in there.
All right, can people at home hear me?
Yep.
Yes.
Can you hear me?
Yes.
Perfect. Creston's going to explain what we're doing as far as how to fill out the tables and why we circled certain things on the screen.
So, okay, so you're plotting PFA versus PD, and PF is this, the top right corner of your confusion matrix, and that's reported on the SIGDET MATLAB GUI as your 1 to 0 errors. Like when you generate signal, it'll show 1 to 0 equals whatever. So that's PF, and then
Oh,
PD
okay.
is the probability that there was a 1 and then you classified it correctly. So if you know, like for A, your A priori probability is 0.25. So you're assuming you're going to get 25 zeros, 75 ones. So if you want the probability that you got a 1 and classified it correctly, it's 75 minus however many 1 to 0 errors you had. So if you have like 10 1 to 0 errors, then you classified 65 ones correctly. So your PD is 0.65.
Does that make sense?
Yeah, I'm just trying to pull up I can't get the code working. I'm trying to pull it up on MATLAB online. I can't paste, which is stupid.
Okay, so I ran the first one and got 17 errors, and 16 of those were 1 to 0 errors. Can you say again how to use that?
So 16 were 1 to 0 errors?
Yeah.
Okay, what was your A priori probability? Your P x equals 0, did you put in 0.25?
Yeah.
Okay, so then you expect there to be 75 ones. So rather than counting them all up, you just assume that there were 75 ones in the actual input.
Mhm.
And then you said there's 16 1 to 0 errors.
Mhm.
Okay, so then your PD is going to be 75 minus 16. So it's 0.59 is your PD, because you correctly classified 59 of the 75
Oh, okay.
ones. And then your PF is just going to be the 0 to 1 errors. So how many zeros did you miscall a 1?
Oh, okay. And that's the 0 to 1, right?
PF is 0 to 1.
Okay. Right. I got 1 when I ran this.
Okay. So then you have, your PFA is 1 and your PD is, well, not 1, it's 0.01.
Right.
PD is 0.59.
Right.
Okay, so then we do that for multiple different thresholds and then we plot them on the same.
Yes.
Exactly. Case A through D.
Okay, so to plot these, then we would go like up 0.59 on one axis and then out like point whatever on the other and just connect the line or connect the dots.
I think you try a bunch of different thresholds.
But I mean on the actual plot itself, right? Like on the y-axis, there's PD, and then on the x-axis, there's PFA.
I think that's right.
All right, can you list out the errors for us so we can, I don't have my MATLAB working, so.
All right, we'll leave you guys to do it. And Preston and I are going to work on our.
Okay, we can probably go to the other breakout room again.
Okay, yeah, I'm good to move to the other one.
Okay.
I'd like you to finish this up at home, get that submitted as soon as you can. I give an official due deadline of midnight tonight.